Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah, we meet again this first week. Okay, so this is chapter number 1, flexibility method. So for this session, I will divide into 2 parts. Okay, the first part I will go through with you about the flexibility method concept, about the redundant concept, the principle of superposition, what is primary structure and redundant structure. And the next 1 hour session, we will derive the compatibility equation, which is the equation to determine the redundant force. Okay, so the learning outcome for flexibility method. As I mentioned, the flexibility method is one of the method to determine or to analyze indeterminate structures. Okay, so when we need to use flexibility method, it is whenever 3 equilibrium equation is not enough, so we have to apply the flexibility method. So the idea is when we cannot analyze unknown reaction because more than 3 unknown reaction in the system, so means that the system has redundant, and we have to solve for the redundant first. Then only we can solve the remaining 3 unknown reaction. Okay, the redundant will be determined by applying the principle of superposition. The principle of superposition, that is the one that we will you will be learning in the next 1 hour session. Okay, we focus on the student learning outcome, as I mentioned to you in the next class. So always begin with the end in mind, means that we have to understand the outcome, the objective, the destination, the goal. Okay, so of course we will start with calculating the degree of indeterminacy, and it is very simple formula. It is just the difference between unknown reaction and 3 equilibrium equation for beam and frame. In truss, we have to consider member force as well. Okay, so degree of indeterminacy is very important to determine because it gives us number of redundant in the system, in the structure. Okay, and then we have to identify the redundant. So the redundant, we cannot simply remove anyone that we like, because in order to determine the redundant, we have to understand the support concept. The support concept, whenever we want to remove one from fixed should the fixed support, the one that we should remove is moment, so that the fixed can fixed support become pin. One remove from fixed become pin, for example. Okay, if we want to remove one from pin, means that pin become roller. If we want to remove one from roller, we remove roller, means it become cantilever end. So we cannot simply remove anyone, because we have to make sure the one that we remove, after we remove redundant, it's still maintaining the stability of the structure. It must be stable, and it must be determinate after we remove redundant. Okay, so we identify redundant, and redundant that we identify, we will remove from the system. And we will determine the redundant by solving the compatibility equation. So compatibility equation is actually the equation the equation to complete the analysis, because when we have 4 unknown reaction, only 3 can be solved using equilibrium equation. So the other one will be the compatibility equation. So to analyze indeterminate structure reaction in indeterminate structure, there will be equilibrium equation and compatibility equation. And compatibility equation is actually come from what we call as principle of superposition. Okay, and under the principle of superposition, we will have the primary structure and the redundant structure. Okay, and by solving the compatibility equation, is actually based on the principle of superposition, focusing on the displacement which is located at the redundant position, and solving the compatibility equation will give us the redundant. the redundant. And once after redundant have been determined, then only we can determine remaining reaction in the structure using either principle of superposition or equilibrium equation. Okay, there are two types of indeterminacy, DOI. DOI, there are two types. One is called as external indeterminacy. Another one is called as internal indeterminacy. For beam and frame, it is just external indeterminacy because redundant is come from support reaction. Whenever redundant is come from support reaction, it is called as external indeterminacy. We have another one called internal indeterminacy, and it is occur in for truss system only. For truss system, and in truss system, it can have external indeterminacy, it can have internal indeterminacy, and it can have both external and internal indeterminacy for two redundant case. Okay, of course, this is there are two types, as you should know, already know. There are two types: determinate structure, indeterminate structure. Another one is unstable, right? Less than 0 is unstable. We cannot have unstable structure. We must remain the structure at least determinate structure. But to have strong, to have more strength, we have indeterminate structure. Okay, indeterminate structure, DOI is more than 0. Okay, why DOI is important? Because it reflects the complexity of the structure, of course. Okay, so understanding DOI is very important. It's very important. Actually, from DOI we get redundant, and then from redundant we can solve for the we can analyze the whole indeterminate structures. Okay, so there are 4 types of structure covers in flexibility method. The first one, for flexibility method, we start with beam analysis, followed by frame analysis. Frame analysis, actually frame has combination of bending and axial effect. However, for beam, we only consider the bending effect. So beam, so truss, not truss, frame and beam has similar analysis. Frame and beam has similar analysis, even though frame may be complex compared to beam frame, but still we analyze using the same principle. Frame and beam has similar analysis because we consider the bending effect in frame, so the analysis is similar. Okay, in reality, frame has combination axial and bending effect, but frame for flexibility method, we just consider the bending effect only. Means that if we have learned about beam, we should be able to solve frame problem directly. Okay, and then for truss, of course, because the axial effect in the truss, so we have to understand about the axial effect, the member forces in the truss. So the formula is also different. So truss has different, same procedure but different in calculation. Okay, so this is the basic about flexibility method, the idea, the concept introduced by this person. Okay, so beside flexibility method name, it is also known as force method. Force method. So in the textbook, I have actually put the ebook, the ebook in the OneNote. So please refer to your OneNote under this under 20244 indeterminate structures, because I combine 2 codes here, 521 and 527. So I have actually put the ebook for this method under force method. In the textbook, it refers as force method. It is also called as compatibility method. Okay, we must understand what is redundant. Okay, we have to choose the right redundant. Then we have to remove redundant. We have to remove redundant. Then after removing redundant, the structure become determinate structure. And the structure after removing redundant is called as primary structure. And the primary structure is determinate structure. Okay, for the procedure, start with identification of degree of indeterminacy. Simple, right? It is just the difference between unknown reaction and 3. So it is equivalent to 1. So 1 is degree of indeterminacy. 1 representing redundant, number of redundant in the system. DOI is equal to 1. 1 redundant is 1, and we have to choose redundant. We have to choose redundant and remove redundant. We have to choose redundant to be removed from the system. So the structure, the structure after removing redundant is called as primary structure. The structure after removing redundant is called as primary structure. So for the analysis, we will analyze primary structure. Primary structure, there are two systems to be analyzed. We will analyze primary structure and redundant structure, and both are determinate structure, not indeterminate anymore. Okay, so we will remove the redundant. Okay, and after that we have to apply the compatibility equation. We have to apply the principle of superposition to derive the compatibility equation. And compatibility equation is actually the displacement at redundant position. Displacement corresponding to the remove redundant. Displacement at redundant position. Okay, and then actually superposition method is actually superimpose effect. Superimpose effect. That's why we have two systems. Original, actual structure, actual beam, we have, it is one system. But this indeterminate structure, in order to solve for the redundant value, we will use superposition, superimpose effect. So we have the primary structure, the determinate structure, plus redundant structure. So both determinate and redundant structure, both are determinate structure. So we will analyze these two structure for one redundant. For one redundant, we will have two determinate structure to be analyzed. Two determinate structure to be analyzed. One redundant. If we have two redundant, we have three determinate structure to be analyzed. Okay. Okay. This is for you just to read. So this note, I have put the link in the Telegram, right? Okay, this is about the key characteristic for analyzing indeterminate structures. And this is the key step: identify and remove redundant forces. And then we will analyze two determinate structures. It is called as primary structure and redundant structure. Okay, when we apply the principle of superposition, we will have the compatibility equation. The compatibility equation is actually based on displacement displacement at redundant position for all types of structure. And then by solving the compatibility equation, we get the redundant. So once after we get redundant, the redundant value, then we can solve the remaining three unknown reaction. Okay, that's the principle. Okay, so let's move to, okay, this one. This is the ebook, the textbook that I have mentioned just now. Under the textbook, it is called as force method. Force method. Okay, so please refer to this one. And I have also put here under the flexibility method. So this is all discussion page that we have, not only for our group, so all groups, group B, group C, as well as group A. So all here. So you just can refer to anyone that you want to refer. Okay. So the module is here. The module. Okay. Of course, there are many, but not yet. Here I will put it later on. So this is the module for the flexibility method. Okay, anyway, the module, the notes, the textbook, and whatever, it is just for you to read. Okay, use that to read using your preparation time, your self preparation time. Remember, 3 hours lecture means you have to spend another 3 hours for your preparation time. So before and after, so use the time to read notes and so on. But during the class session, I will normally talk and talk. Okay, so please listen carefully, watch and listen carefully to So just focus on the screen, yeah. Okay, so this is the notes. So basically, as I mentioned, whatever that I said during the class session is written in these notes. Okay, so this is for your refreshment. Okay, read to understand more. Okay, so now I have prepared this one blank screen. Okay, just focus on what I will try to explain. So the first part of this session, I will focus on how to identify redundant, understanding redundant, characteristic of the redundant. Okay, about the concept of principle of superposition, how to get the compatibility equation, what is the primary structure, redundant structure. So will be explained here right now. Okay, so the idea is, okay, we will start with beam analysis first. And please look at this carefully, because understanding of this beam is actually the same with frame, the truss, and so on. So normally for the derivation, for the first part of flexibility method, I will only explain the concept using beam analysis. And then once we understand about all the process, the procedure using beam, I believe you can use the same procedure, the same principle for remaining, for frame, for truss, and so on. Okay, so we start with beam. Okay, I will start, of course, with determinate structure. In beam analysis, there are two types. There are two types of beam. It is called as cantilever beam and simply supported beam. You have learned this in solid mechanics. It is cantilever beam and it is simply supported beam. Okay, there are two types of determinate beam here. One is cantilever beam, another one is simply supported beam. Let's say this is subjected by UDL. Okay, so A, B, A, B. Okay, so looking to this, the first one first, the first diagram first. Okay, so at A is fixed support. At fixed support, we understand that there are three unknown reactions at fixed support. 1, 2, 3. And these three unknown reactions can be determined, can be solved using three equilibrium equations. Okay, that's the idea, that's the principle. Okay, same goes to simply supported beam. Pin support has two unknown reactions, and roller support has one unknown reaction. And these three unknown reactions in simply supported beam can be determined using three equilibrium equations. So these are the principle, the basic principle of determinate structure. Determinate structure. So for these two determinate beam, the degree of indeterminacy is DOI 3. Unknown can be solved using three equilibrium equation. So it is 0. So this is determinate structure. This is determinate beam. Okay. So I believe everyone have understand about this. Okay, now we move to indeterminate beam. Okay, in indeterminate beam, let's say we have the same beam. Okay, one is fixed end, but another one is roller end. Okay, same loading. Same loading, UDL for example. Okay, same support A, not same support, A is fixed, now B is roller. Okay, we understand that fixed has three unknown reaction. So 1, 2, and 3. And another one come from B, roller at B. So in this beam, there are 4 unknown reaction. There are 4 unknown reactions. So DOI, there are 4 unknown reaction, and only 3 can be solved using equilibrium equation. So it is 1. So DOI, degree of indeterminacy for this beam is 1. 1. Okay, 1. So what does it mean? It means there is one redundant in the system. One redundant in the system. Redundant is 1. So 1 redundant. 1 redundant. 1 redundant is the problem. 1 redundant will be determined first. 1 redundant will be determined first. So R will be chosen. So there are possibility. There are two possibility because there are two types of determinate beam. There are two possibilities of redundant here because there are two types of determinate beam. We have the first type is cantilever beam. The second type is simply supported beam. Because the idea is after removing the redundant, okay, we will get either cantilever beam or simply supported beam. Okay, so for example, if we want to have cantilever beam, the one that we should remove is BY. So after removing BY, remove roller, it becomes cantilever beam. And the cantilever beam is called as the primary beam. The primary beam. The beam, the structure after removing redundant is called as primary beam. Primary beam. Okay, if we remove MA as the redundant, okay, we will have simply supported beam. Simply supported beam if we remove moment at A. Okay, so instead of, okay, we have MA, we have BY, no, A first. We have MA, we have AY, we have AX, we have BY. 4 unknown reaction, right? This is 4 unknown reaction. This is 4 unknown reaction. Okay. For all these 4 unknown reaction, we want to remove one, but we cannot simply remove anyone that we like, cannot. Because we have to make sure that after removing redundant, we will have either cantilever beam or simply supported beam. Simply supported beam. It means that we cannot simply remove AY. Because removing redundant reflect to the support condition. Support condition. Fix when we remove one, fix like this, right? Fix ni, this is fix, right? Fix support. So fix support, when we remove one from fix, we will have pin. This is pin, right? And pin support, if pin support, we remove one from pin, we will have roller. This is roller. And if we have roller, we want to remove one from roller, okay, it become cantilever. Cantilever N. Okay, start from fixed, remove one, become pin. If it is fixed, we want to remove one, it become pin. If it is pin, we remove one, it become roller. If we have roller, we remove one, it become cantilever N. So that is why we cannot simply remove AY. AY cannot be the redundant because it do not represent any one of these type of support. AX cannot be the redundant because of the same reason. So there are two possibilities because we have two types of determinate beam, cantilever beam and simply supported beam. So every time when we want to remove redundant, make sure we have stable and determinate structure. stable and determinate structure. Okay, we can have By as redundant. We can have moment as redundant. Means that there are two possibilities. Two possibilities of redundant. We can have By, we can have moment at A. Okay, so this possibility can refer to the redundant and also the primary structure. Okay. Okay, so when we have just now this, okay, indeterminate beam, and if we choose By, if we choose By as redundant, so we have cantilever beam. If we choose moment at A as redundant, we have simply supported beam. Simply supported beam, loading is there. So this one, whenever we choose moment as redundant, moment at A as redundant. Okay, so the first one is cantilever beam. The second one is simply supported beam. Both are determinate and stable. Okay, so we call this two diagram, cantilever beam and simply supported beam, as two possible primary structure. Okay, there are one redundant means one redundant will have two possible primary structure. One redundant. Two possible primary structure. Okay, so this is primary structure. This is primary beam. This is also primary beam. One is cantilever beam. One is simply supported beam. Okay, so the first one, the cantilever beam is whenever By is the redundant, and the simply supported beam is whenever Ma is the redundant. That is the idea. So it is not only for beam, same understanding we have to put to frame analysis, truss analysis, same. Okay, for example, if we have frame, where frame with one fixed, one roller. Okay, here is A, B, and C. Let's say it is subjected to UDL along member BC, like this. So this is indeterminate frame. Indeterminate frame. Okay, looking at the support, there are four unknown reaction. There are four unknown reaction, and only three can be solved using equilibrium equation. So there is one redundant in the system, one redundant in the frame. So this one redundant, we have to choose the redundant and we have to remove the redundant. And the structure, the frame after removing redundant is called as primary frame. Okay, there will be two possibility because we have C as a roller at C. So when we remove roller at C, we will have cantilever N at C. So Cy as the redundant. It is stable, it is determinate, because one stable structure must have at least three unknown reaction. It cannot be two. Okay, and we can also have moment at A as redundant. Moment at A as redundant means we remove one from fixed, so it become pin. So let's say this one, let's say the redundant is MA. The redundant is MA. So when we choose moment at A as the redundant, fixed become pin. Fixed become pin. So now we have frame. Okay, fixed now become pin. roller remain. So this is determinate frame. This is determinate frame. Loading is still there. Okay, A, B, C. This is determinate frame after removing moment at A. Moment at A. So this will be the first possibility. The first possibility, because the second possibility is whenever we remove CY as redundant. Okay, so the same principle we apply into frame. So what if truss, for example, truss also, let's say we have this. Okay, let's say we have this. Okay, loading like this, for example, 100, 200. We have A, B, C, D, and E. Okay, we check for the degree of indeterminacy, and of course for truss, degree of indeterminacy, we use another one formula, M plus R minus 2J. Because in truss, we can have internal indeterminacy. We can have internal indeterminacy. So M plus R minus 2J. And for this truss, it is M 1, 2, 3, 4, 5, 6, 7. 7, right? Is it 7? 1, 2, 3, 4, 5, 6, 7. M is 7. R is 4. 7 plus 4, 11. Minus 2J. 2J. 2 times 5. 2 times 5. 2 times 5. So we get 1 here. Okay. So this one to check whether it is external indeterminacy or internal indeterminacy, we can check using the support. Because to get stable structure, for the truss, it must have one pin, one roller. One pin, one roller. So one pin, one roller means that we can have one reaction, one redundant S reaction. Okay, in this case, we can check 4 unknown reaction and only 3 can be determined using equilibrium equation. So 1. So this means that the redundant is come from support. There will be another case where member forces is the redundant. It is for internal indeterminacy. Okay, when we have like this. 1 and 2 here. Okay, so here is pin. This one is roller. So same loading. Label 1, A, B, C, D, E. Okay, now if we check for DOI, it is M is now 8. Because we have another member for AC, plus reaction is 3, because 1 pin, 1 roller here, and then joint is 5. So total is also 1. But this time, please check for the external, whether it is external or internal indeterminacy. Okay, check by finding the difference between unknown reaction. How many unknown reaction? It is 3 unknown reaction. 3, 0. That's mean we cannot remove redundant from support, because there will be no truss, stable truss with 2 roller, cannot. So the stable structure must at least have 1 pin, 1 roller. One stable truss, stable and determinate truss must at least have 1 pin, 1 roller. So in this case, we cannot remove 1 from reaction. So the one that we should remove is the member force. So this is internal indeterminacy. Internal indeterminacy. Okay, So this one is external. External indeterminacy. Okay, external indeterminacy means the redundant come from support reaction. The redundant come from support reaction. Okay, but the other one, the redundant come from member force. Come from member force. So that's the difference between external indeterminacy and internal indeterminacy. Okay, so in this case, in the first thrust case, so redundant can be AX as the redundant, or can be BX as redundant. So that once we remove AX, pin become roller. Pin become roller. So this is the case. But for the second diagram, the second thrust, we cannot remove one from A, because if we remove one from A, from this roller, we cannot remove one, because if we remove this, it become roller. So there's no thrust with two roller as stable thrust, cannot. Okay, so the stable thrust must have at least one pin, one roller. So we cannot remove support reaction as the redundant. So here the member force will be removed. Okay, so in this case, R is member force, F at member, A, C as the redundant. So this one is internal indeterminacy, and this one, whenever AX is the redundant, is external indeterminacy. Okay, so we just remove the redundant. Okay, do you get the idea? Okay, let's say we have one beam like this. Okay, now roller here, we have one UDL here. Okay, so let's say this is 10 kilonewton per meter. We not solve the value. It is just to explain to you the concept first. Okay, here we have one indeterminate beam, A, B, C, and D. C and D. Okay. Three cutting section here. Okay, so this beam is indeterminate beam because there are four unknown reaction. And only three can be solved using equilibrium equation. So there will be one redundant. So this redundant, okay, let's say if we want to analyze cantilever beam, so we should remove dy. If we want to remove moment at A, so we will get simply supported beam. So you can see here that name of the redundant will change depending on the redundant that we choose. Okay, now let's say we choose dy as the redundant, means that we remove dy. So the structure, the beam after removing dy is cantilever. Remain all external loading. The one that we remove is dy. The one that we remove is dy, and it is actually like this. The one that we remove. So we have the first here is called as primary beam. So where the dy, where is the dy that we remove? We put into another system that is called as redundant beam. Redundant beam. Okay. One is primary beam, another one is redundant beam. Okay, actually this fulfill what we call as principle of superposition. It is called as principle of superposition. Superposition. So original indeterminate structure is actual beam. Then we choose redundant, and removing redundant give us primary beam. Okay, and primary beam is determinate beam, and it is not equal to actual. Only after we plus with redundant beam, it is actually combination of external loading and dy, then only we get back all that we have in actual beam. So this fulfill the principle of superposition. So under the principle of superposition, as I also written in the module, okay, we have to remember one general equation. Okay, for understanding the principle of superposition, we have to understand one general equation. So this is general equation based on the principle of superposition. So this general equation states that actual structure is equal to primary beam plus redundant structure. Okay, this is the general equation which is based on the principle of superposition. In actual, the question given is indeterminate structure, indeterminate beam, for example. In indeterminate beam, so this is indeterminate structure. In indeterminate beam, okay, there are 4 unknown reactions that cannot be solved, cannot be determined using only equilibrium equation, cannot. So what we need to do is we have to apply the principle of superposition. Okay, so the idea is we use superimpose, just like superimpose, where we remove by and we put back by in another diagram. Okay, just like this. Okay, so the structure after removing redundant is called as primary structure, and primary structure is determinate structure, and we have to apply back by into one system, same type. If the primary structure is cantilever beam, the redundant structure also cantilever beam. If the primary structure is simply supported beam, the redundant structure also simply supported beam, same type. We have 2 determinate structure, same type of beam with different type of loading. So primary structure, just remove dy, and redundant structure, we have one structure, one cantilever beam subjected to by, subjected to dy, in this case dy, subjected to the redundant. Okay, so that's the idea of the the principle of superposition. Okay, so looking at this diagram, primary beam and redundant beam, actually it's similar with the one that you have learned under determinate structure, under deflection topic. Can you recall something here? About the primary structure and redundant structure, we have one determinate structure here where it is subjected to all external loading, and we have one structure, the cantilever beam subjected to actually this one which we change to 1 times dy subjected to a unit value. Okay, a unit value of dy. Okay, so the redundant beam, because dy is unknown, so when we cannot analyze the structure subjected to dy, we have to change to 1 times dy. So in the analysis later on, we do not analyze the redundant beam subjected to dy, but we will analyze the redundant beam subjected to a unit value of dy. A unit value yang ni of dy. A unit value of dy. So we will analyze one determinate structure where it is subjected to all external loading, and we will analyze one cantilever beam without any loads except one. Okay, please recall when we have one cantilever beam subjected to, for example, here 10 kilonewton per meter. This is A, this is B, this is C, this is D. Okay, and we have another one, okay, and subjected to a unit value. Of dy dekat sini. Okay, so we have A, B, C, D. Because we have to remain 3 cutting section. Okay, my question is, okay, if this one is primary structure, this is primary structure, primary beam, it is cantilever beam, and another one is redundant beam, what you see from these two diagrams? Is it similar with something that you have learned, the characteristic? Is it similar with previous topic in determinate structure?
Yes.
What is the topic? Okay, primary beam. Look at the characteristic. It is determinate. It is a cantilever beam subjected to external loading, subjected to real loads. So previously, you have learned this with the same characteristic. You have analyzed same type of beam with the same characteristic. What is the name of the beam? What is the name of the beam with the same characteristic? With primary beam. Can I have your answer? Pernah belajar dalam determinate structure, right? Under topic displacement. When we have to analyze two systems, what is the system? Two systems with the same characteristic. Real system. So primary system is just like the real system. And another one? Virtual system. It is just like, it is not 100% similar, it is just like. Okay, because the characteristic of primary beam, it is a cantilever beam subjected to all external loading. And for the second diagram, the redundant beam, okay, because we have take up dy, because it is dy equal to 1 times dy, 1 times redundant. Okay, so when we analyze, we just focus on a unit value. So for redundant beam, it is just like virtual system. It is just like virtual system because it has same characteristic. It is a system, it is a determinate system, determinate beam subjected to a unit value. Cuma this time, we have a unit value of dy. A unit value of dy. Okay, same characteristic. Okay, so to analyze later on, any type of structure, we will have to analyze two system, two structures like this. We will have primary beam, primary frame, primary truss, primary structure. And in primary structure, it is determinate structure, and the system, the structure has all external loading, all real loads in the system. Okay, we have to calculate reaction. We have to write moment equation. calculate reaction, then write moment equation, then only we can determine displacement. Okay, and we will have to analyze the now the redundant structure. It is just like the virtual system. Virtual system is when the system or the structure without any load except a unit value. So same goes to here. So without any load, without any other loads except a unit value. It is a unit value of redundant. It is redundant beam, redundant structure, and it is determinate and stable. Okay, so both of these beam, okay, must have same characteristic, not characteristic, same beam, same type of beam, same type of beam. If the primary beam is cantilever beam, so redundant beam also same, it also cantilever beam. If primary beam is simply supported beam, same, redundant beam also simply supported beam. Another thing is, if in the primary beam, they have 3 cutting section, A, B, B, C, C, D, 3 cutting section, also redundant beam must have the same, because we want to times. Whenever we want to solve for the displacement, we have to integrate the same section. We have to integrate the same section. So we have to remain 3 cutting section in redundant beam, even though, okay, we just see that A to D is just one beam, right? AD, just like that. But still cannot. We have to pecah, okay, divide into 3 cutting section as well. Follow redundant primary beam. Follow the section in primary beam. Okay? Okay, do you understand about degree of indeterminacy, about redundant, about choosing the right redundant, about the possible primary structure? So which one should be the redundant? Principle of superposition, the general equation, and about the primary structure and redundant structure. Do you have any question? Do you have any question? Before we move to the second part of this lecture? No, no question. Okay, if there's no question, I think we take a break for 5 minutes. So we will come back at 11:15. Okay, for session after this, we will actually derive the compatibility equation for one beam problem. Okay, so we take a break for about 5 minutes. So we will meet again at 11:15. Assalamualaikum warahmatullahi. Can we continue?
Yes, Madam.
Okay, so we focus on the principle of superposition. The principle of superposition states that actual beam is equal to primary beam plus redundant beam. So this is the diagram which is taken from the textbook. Okay, this is the case where it has 1 point load here at the center of the beam, one fixed, one roller, actual beam. So BY is the redundant. So in the primary structure, we remove BY. We need to remove BY. So after removing BY, the primary structure is cantilever beam, and actually as I mentioned in the slide as well, the principle of superposition is actually based on displacement at redundant position. If BY is the redundant, means that the position is B. So means that we have to focus on the displacement at B for all types of structure. We have actual beam, so we have to mark the delta, the deflection at B in actual beam. We have to mark the deflection at B in primary structure, and we have to mark the deflection at B in primary structure. Okay, for the primary structure, after removing redundant, it is like this. Okay, primary structure, it is a cantilever beam subjected to point load or any type of load, doesn't matter, subjected to external load. Okay, it will deflect. And because it is cantilever beam, and we mark the delta deflection at point B, as delta B naught. Okay, so this delta is deflection. This is deflection at position B. This is deflection at position B. Okay, for deflection, this is deflection. Delta is deflection, displacement or vertical displacement at point B. At point B, 4. For naught is always the symbol used for primary structure. Naught, B delta B naught, delta C naught, delta D naught, delta 1 naught, delta 2 naught. Naught used here represent the primary structure. So delta B naught is actually delta or vertical displacement at point B for primary structure. Naught is the symbol for primary structure. Okay, so due to loading, due to external loading, the cantilever beam deflect, and we mark the delta at point B for primary beam as delta B naught. So we will determine this delta B naught. Okay, it is primary beam. It is primary beam plus redundant beam. So we have another one. It is redundant beam. And to be specific, we use the name of the redundant as BY applied. BY applied means when we put BY into back into the system, we do not put roller, but we assume that it is one applied load named as BY. It is applied load named as BY. We apply into the cantilever beam. So it is a cantilever beam. It is a cantilever beam subjected to an applied BY. So this redundant beam is named as redundant BY applied. Redundant BY applied. So the name will be changed based on the redundant chosen. If CY is the redundant, it is called as redundant CY applied. If DY is the redundant, it is called as redundant DY applied. Same goes to moment. If moment at A is the redundant, the system, the redundant beam is called as redundant MA applied. Okay, to be specific. So this is redundant beam. And due to an applied BY, okay, forget about roller at B too. So just imagine that this is an applied load BY. So due to an applied load BY, so the cantilever beam subjected to BY will also deflect. But this time BY, because of the roller reaction at B, so the direction is like this side, upward direction. So we just follow that. Okay, due to an applied BY, the beam is also deflect, but it deflect upward. Okay, again, we mark the displacement, the deflection at the redundant position. We mark the deflection at redundant position. So if we use here BY, means that it is delta. Delta, again, the notation used has meaning. Delta BB means the first notation is position, the second notation is type of beam. Type of beam. The first notation at point. The first notation is the position at point B. Delta at point B. The second B refers to this B. Redundant BY applied. So delta BB is deflection at position B for redundant BY applied. Delta BB. But we cannot analyze cantilever beam subjected to BY, right? We cannot analyze this beam subjected to BY because BY is the unknown. So in order to analyze this cantilever beam, what we need to do is we change BY to 1 times BY. 1 times BY. So whenever we change this, BY equal to 1 times BY, delta also change. So the delta is now changed to FBB. FBB here, FBB times BY. So FBB, so the delta BB changed to FBB times BY. Okay, now it is FBB times BY. So for the analysis later on, you do not need to put BY into the redundant system. Just put a unit value. A unit value. So all displacement in redundant structure, redundant beam, we will not label as delta BB, but we label as F. We will label as FBB. FBB. We will label as FBB. All displacement due to a unit value, displacement due to a unit value will be labeled as FBB. Displacement due to a unit value of BY will be labeled as FBB. So that is why previously we have okay, for example, let's say we have one beam. Okay, one beam, one roller. Okay, 1 point load, 1 UDL. Okay, you can create beam, simply an indeterminate beam like this. So just put loading wherever you like, the value, whatever value you like. type of loading, whatever type you like, and then the process will be the same. Okay, let's say this there is the point load 100 kilonewton. So let's say this UDL is 20 kilonewton per meter. Okay, and then you can put the length, whatever value you like, to practice to understand about flexibility method and to solve the problem regarding flexibility method. A, B, C, and D. Okay, so we have to mark B as 1 point. We have to mark C as 1 point. Okay, because whenever we want to write moment equation later on, we have to analyze. We have to have one cutting section for AB, one cutting section for BC, one cutting section for CD. We cannot have one for AC. Cannot. Even though the label is not given. So let's say the label is not given. It is just like this. It is just like this, for example. Still, you have to put C and D, because labeling of this will be depend on the how many cutting section we will analyze later on during the moment equation process. Okay, we have to have 3 cutting section, because it go back to understanding about the process of moment to moment bending moment diagram, writing moment equation, then calculate bending moment. We will start with writing moment equation. So it will go back to that principle. Okay, so let's say we have this beam. Okay, this beam. If we have 1 DOI, okay, 1 DOI, come from 4 minus 3 is equivalent to 1. Okay. So if we want to have cantilever beam as the primary beam, so we choose redundant, BY as the redundant, and so having this as redundant, we know that we want to remove BY as redundant. We want to remove BY as the redundant, and by removing BY, we will have primary structure and redundant structure as cantilever beam. Okay, so we apply principle of superposition. Where it states that actual beam equal to primary beam plus redundant beam. And to be specific, we can write here redundant BY applied. Okay, the principle of superposition. Actual beam equal to primary beam plus redundant BY applied. BY is to be removed from the system. So we have we will have primary beam plus redundant beam. Okay, I like to have like this first. Okay, so I have like this. This is actual beam. So actual beam using the principle of superposition. This is actual beam. And this is equal to primary beam. This is equal to primary beam Okay, so for the primary beam, we remove this roller. Okay, this is primary beam. This is primary beam. This is primary beam. So the only one that we remove from primary beam is the roller, primary beam. Okay, so we refer to this principle, yeah. Okay, primary beam plus redundant BY applied. Plus redundant BY applied is okay, no external loading, because external loading is here already. It is 100 plus 100, then only we get back 100 in actual beam. Okay, the idea is 100 from actual beam is equal to 100 plus 0. Okay, so there is no UDL as well. Okay, so the 220, the 20 in actual beam is equal to 20 plus 0, so remain 20. Okay, now in this redundant beam BY applied. This is redundant beam. Okay, we use the specific label, specific name. We mention the redundant in the redundant beam system. Okay, so it is a cantilever beam subjected to a unit value of BY. So BY that we remove from we remove from the system, we put into the redundant beam, and since BY is the unknown, so we cannot analyze BY. So what we will do is we will analyze a unit value of redundant. So the diagram of redundant beam is look like this. So a cantilever beam subjected to a unit value of BY. Of BY. BY ni for the whole of BY, not only a unit value, the whole value in the system times with BY. So it is like this. So if we refers to deflection occur in this redundant beam, it deflect like this. So we mark this displacement as FBB, not delta BB. FBB. Here is FBB. This one is FBB. Due to a unit value, this is FBB. Okay, it is also displacement. Deflection at position B due to a unit value of BY. So the first notation, this is displacement. This is position. This is type of beam, BY. Okay, F, because this is for redundant. Because due to a unit value, we use all F. Okay. So for the primary beam, for the deflection, deflect. But we just need to measure or mark the delta at B, at position B. We mark the delta at position B here. Okay, so this will be labeled as F, as delta at position B for primary beam. Delta at position B for primary beam. Remember, it is delta, the deflection. The first notation for the position. The second notation for type of beam. It is primary beam. All primary structure we label as node. Delta B node is for the primary beam. Delta C node is for primary beam. Delta B node. Delta deflection at position B for primary beam. Okay, redundant BY applied. because of the unit value. So we use F because delta BB is FBB times BY. Okay? Yang ni tadi. So due to a unit value, delta is marked as F. The deflection is marked as F. So it is F. F, the first notation B, the first B. FBB, the first B is for the position. The second beam for type of beam. The second beam for type of beam, this is BY applied, redundant beam. So this FBB refers to deflection. Deflection at position B. Deflection at position B for redundant beam. For redundant beam. So this is how the cantilever beam, the redundant beam look like. Okay. So this fulfill the principle of superposition. Diagram like this ada dalam module. Okay, saya dah draw every single thing exactly like this. Okay, actual beam, indeterminate beam given in the question. Okay, primary beam, the only one that we remove is only the roller, the BY, the redundant. And in redundant beam, it is the cantilever beam subjected to a unit value of BY. So due to a unit value of BY, so the delta marked as FBB. FBB means deflection at position B for redundant beam. Okay, so since the compatibility equation is actually displacement equation, but we don't say displacement equation. We say as compatibility equation. The compatibility equation will be written based on the redundant position. The redundant position. Okay, the redundant position refers to B. Okay, refers to B. Okay, refers to B. The position for each system. Okay, so we write the compatibility equation using the principle of superposition, focus on the displacement at redundant position for all systems. Start with actual beam. Actual beam, it is delta. In actual beam, it is actual beam equal to primary beam plus redundant beam. In this case, is redundant BY applied. Okay, delta at point B in actual beam is delta at B is equal to 0 because of the support. Delta at B is equal to 0 in actual beam because of the support. So this is delta B. So, okay, based on this, it is delta B. And in primary beam, it is delta B naught. We can recognize delta B naught is for primary beam because of the naught symbol. Okay, and plus redundant BY applied. So all redundant system, displacement used is F. All redundant system. Lepas ni jumpa macam-macam. Semua pakai F. FBB. Now, it is FB because yang ni refers to position. The first refers to the position. The first notation refers to position. Second notation refers to type of beam. Redundant BY applied, we use the B label so to be put here. So we have delta for all three structure. Okay, actual beam, the delta at B is labeled as delta B, deflection at B labeled as delta B. In primary beam, the label will be used is delta B naught, and for redundant BY applied, deflection we need to change to FBB. The first notation is for the position, and the second notation is for type of beam. So FBB is deflection at position B for redundant beam. So from this, this is displacement, this is the compatibility equation, but it is not final yet, because we want to have one equation which is equivalent to 0. Equivalent to 0 refers to actual beam where the displacement is 0. So now we apply 0 here because of the support, and we rewrite the compatibility equation again. So the compatibility equation is now, so since normally when we write equation, we want equation equal to 0. We want something equal to 0, right? We do not write 0 equal to something. So we change position, we start from primary. So primary is delta B naught plus FB, so I forget something here, BY here. FBB times BY is equal to 0. Okay, so this one, FBB times BY, because it represents delta B. Okay, so the compatibility equation for this beam, for this question, is delta B naught plus FBB times BY. This is the compatibility equation. This is the compatibility equation. So, actually, so whenever we choose different redundant, for example, actually, if, for example, if MA is the redundant, we can have the compatibility equation directly using the same format of compatibility equation. Okay, so for MA, remember moment, the partner is theta. Okay, we cannot get rotation, we cannot get moment from delta. Okay, so moment, the partner is theta. So when moment at A is the redundant, delta is now theta. Okay, theta, rotation. Position is A. Yang ni position A. Position A means we need to label as A here, A naught. So we just change from delta to theta. Position we change from B to A because moment is located at A. Naught remain. It is representing the primary system. The primary system plus F remain for the displacement, for the rotation. It can be rotation, it can be displacement. F remain in redundant system. And position A, redundant MA, we use A here. So it becomes FAA. FAA times with MA, the redundant. So that is why we use, okay, we use redundant MA applied. So this is also equal to 0. Okay, so this is a compatibility equation when moment at A is the redundant. Okay, so same goes to any type of question. Maybe the position of redundant will be changed. Maybe there will be equation, there will be question where CY is, C is the position, D can be the position, E can be the position. So of course there will be one standard form of compatibility equation. Okay, so now we will change to the standard form of compatibility equation where one redundant is labeled as R1, So because after this we will have R1 and R2. So R1, let's say BY is redundant, right? BY is redundant. So this is refers to R1 is R1 means one redundant. BY is the redundant. Okay, now instead of labeling as B, delta B naught plus FBB times BY is equal to 0. Or instead of writing theta A naught plus FAA times MA, we change to the standard symbol 1. So for the first one, delta B naught, if we choose BY as redundant, all label B will be changed to 1. So now we will get delta 1 naught plus 1 replacing B, F11 R1 equal to 0. Okay, same goes to MA as redundant. We get, because of the moment we use theta, not delta. 1 refers to the position number 1 naught plus F11 times R1 0. Okay, same equation. And normally when we solve the problem later on, instead of using R1 in the equation, I choose to use the right name of the redundant so that we do not confuse about the displacement. For example, if we use BY as redundant, just use BY in the compatibility equation. So delta 1 naught plus F11, if BY is the redundant, just put BY here. So it is equal to 0 like this, so that we know that BY should be delta, referring to the delta. And for MA as redundant, theta 11 times MA. So if we use MA as redundant, this one cannot be delta. We have to change to theta, because we understand that the moment pair with theta, force is delta. So now we put the right one. So in the solution after this, we will write like this. Okay, the compatibility equation. And so all this is actually refers to displacement that actually we adapt and adopt from unit load method as well. So we integrate moment equation. So delta 1 naught is 1 over EI from 0 to L M1 M naught dx. Okay, and theta 1 naught is 1 over EI, not theta. So refers to the first one first, this one. Okay, so F11 is 1 over EI from 0 to L. F11 means M1 square dx, M1 2 times. Okay, so this is the formula. So if we use theta, same formula, but we change to theta. Okay, so these are the formula of displacement. So inside this, there are two moment equation. Dalam this equation ada two moment equation, M1 dengan M0. Dalam ni ada two moment equation. Ada M0 dengan M1. Not is always label for primary beam. And ni redundant lah. Redundant apa? Kita dah pilih redundant tadi. R1 sama dengan BY. So this is redundant. BY applied. Okay. Do you get the idea? About how to derive the compatibility equation? Do you get the idea?
Yes, madam.
Okay. So in summary, actually the derivation is not for you to derive every time we want to solve problem. So this derivation is just for you to understand how we get the compatibility equation, because we can remember, right, the standard form of compatibility equation. So by understanding the compatibility equation, after this we can actually straight away write the compatibility equation directly after we choose redundant. For example, if we want to analyze, for example, if we want to analyze this beam, for example, whatever type of structure. So this is 10 kilonewton per meter. Okay, this is roller. This is 200 kilonewton. Okay, let's say A, B, C, D here. A, B, C, D. Okay, so calculate DOI. DOI is equal to 1. So R1, choose one, either MA or D or CY. This time is CY, right? So now let's say we choose CY as the redundant. So from this actually, we know that the general equation of principle of superposition will be written as, because CY is force, so we know that this should be delta, right? So the compatibility equation directly we can write compatibility equation is delta standard form 1 knot. So this is belong to primary beam delta 1 knot standard form. Okay, plus F11 standard form. Okay, now times with redundant, do not need to write R1, but we better put the redundant directly here. So here is CY equals to 0. So this is the compatibility equation. So whenever we understand about the redundant concept, if we understand that, okay, I'll say this is the beam, this is 4 unknown reaction in the system, there will be 1 redundant. We choose redundant, CY is the redundant, and by choosing the CY as redundant, straight away we can write the compatibility equation, the general form, the standard form of compatibility equation. For CY, it must be delta, displacement is delta. So delta, the standard form, delta 1 knot is for the primary system, and F11 for the redundant system. So F11 mesti times back with the redundant. So F11 times CY. F11 times CY is equal to 0 because of the roller. So this is compatibility equation. So understanding flexibility method is very important. Okay, flexibility method is one of the method to solve indeterminate structures. So when to use this, whenever four unknown equation is not enough to whenever 3 equilibrium equation is not enough to solve for the reaction, so we have to use another equation. The equation is called as compatibility equation. So how to get compatibility equation? So this is the compatibility equation. It is come from displacement. So by solving this compatibility equation, we get CY, we get the redundant. So inside this, we have 2 displacement. Inside this, we have 2 displacement. One is delta 1 knot, another one is F11. What is delta 1 knot? It is 1 over EI from 0 to L. Look at the symbol used. It is M1 M naught dx. And what is F11? What is F11 from 0 to L? This is M1 square dx. So this is the formula to calculate displacement. Inside the formula, there are 2 moment equation. We label as M1 and M naught. And again, M naught, M1, this is for primary beam. And M1 is redundant. What is the redundant? Redundant CY applied. This is R1 because R1 DY. Okay, so we have 2 systems. One is primary beam, one is redundant CY applied. So we will analyze these two systems. Means that, okay, means that this is actual beam, right? This is actual beam. This is actual beam. So when we analyze later on, this beam, we will analyze. The first one is primary beam. The first one is primary beam. The primary beam is without roller support. So after removing CY, it is cantilever beam. And another one is redundant CY applied. Redundant CY applied. So redundant CY applied, no external loading. No external loading. Okay, the roller at C, we put a unit value of CY. So these are the two determinate beam to be analyzed, because the first one, the primary beam, give us M naught, the moment equation, and the second one here represent the redundant CY applied that give us M1. M1. Okay, that is the idea about the principle, the principle of superposition and the flexibility method. Okay, so the idea is we will analyze the moment equation M0 and M1 to be substituted into this formula. So once displacement is determined, these two displacement are determined, delta 10 and F11 put into the compatibility equation. So with these two displacements, CY can be determined by solving this compatibility equation. So then we get the redundant. So having the redundant, we can solve remaining reaction using equilibrium equation. Okay, that is the idea. Do you get that?
Yes, okay.
Okay, I hope you understand, and please spend the 3 hours, about 3 hours for your SPT, student preparation time. Remember, 3 hours contact. 3 hours contact means you have to spend 3 hours preparation before and after class. Okay, do it for revise back what you have learned today. Okay, for next, okay, remember to submit your diagnostic test and also the formative assessment. So this week I do not give you a question for you to answer. Okay, just record 1 minute video to explain about the flexibility method. And then for next week, because next week we have the Bengkel, 1 whole week Bengkel, all lecturers involved. So for 2 hour session next week, next Friday, I will move to night session. And 1 hour session I will replace by with video. And from the video you have to do one question, and you have to submit. You have to submit to me. Okay, the link will be given later. Is it okay with that?
Yes, madam.
Okay, if you have problem, just text me in the Telegram or personal Telegram, doesn't matter. Just text me. Make sure you really understand about the concept of flexibility method, about the principle of superposition, because it is very important. Because once you understand about the whole, actually you can apply the same principle to frame, to truss later on. Okay, actually the same concept, the same formula will be used in frame as well. Okay, so you can start prepare yourself, okay, to be success in this semester for this course. Okay, target A lah, insyaAllah. Okay.
InsyaAllah, madam.
Okay, insyaAllah physical we meet again week number 3 ya. Week number 3. Mohon maaf sebab this 2 week full with bengkel preparation for you all juga. Okay, so insyaAllah. So make sure even though the session is online session or video session, you have to fulfill your responsibility towards each subject you are taken. Okay, so please do your responsibility. Please study. Please do exercise. Okay, to form your understanding. Without exercise you tak boleh faham. Dia sama macam dulu zaman sekolah kan. Selalu cikgu Max dah pesan buat latihan. Daily exercise. So sama juga. Cuma mungkinlah tak perlu sampai daily exercise macam you belajar Max zaman sekolah kan. But still you have to do exercise. Regular exercise, continuous exercise. So that you akan lagi mahir lah. Okay, please do exercise. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Salam madam. Thank you madam.
Thank you, madam.
Thank you, madam.
Okay,
Thank you.
bye.
Salam. Thank you, madam.